Okay, so if not, so let's start. So last time, we talked about, we started talking towards the end of so we did, primal dual for SVMs. And at the end of last lecture, we started talking about, what actually happens in practice, right? We first talked about linearly separable SVMs. They're very limited use. Nobody really uses them because, many times you have a classification problem. You don't know whether it is linearly separable or not, right? So the way SVMs are used is as non-linearly separable SVMs. Okay, so many times when people talk about SVMs, they'll just automatically mean non-linearly separable SVMs. But let's dive into that today's lecture. Okay, so today we'll talk about non-linearly separable SVMs. Okay, and of course, it is support vector machines. Okay. And I'll talk a little bit about, continuing from the material that I mentioned, we started last time. So that is going to be a major part of today's lecture. But then you can actually couple it with something called kernel SVMs that are another way to handle non-linearly separable data sets. So that's what we will talk about today. Okay, so let me recall, the SVM problem. You have points, one from one class, the others from another class, and then you have like a margin. Okay, and then you have some points which are, further away from the margin. Okay, and if I write the SVM primal, that is, minimize over W naught, half of the 2 norm of W square. And this margin, sorry, my drawing is not symmetrical as it should be, but this is 1 divided by the 2 norm of W, okay? And this is equal to this part, okay? And the property that the data is linearly separable. So this is, I'm still talking about linearly separable SVMs in the beginning. Okay, we did that. They should be, all the points should be on either side of the margin. So I have this inequality, and I've put it in kind of standard form for doing the analysis of primal dual. And then when we look at what we have done before is we were able to derive the dual, right, through forming the Lagrangian, minimizing the Lagrangian over x's or w's, sorry. And then we get that the SVM dual is a problem which is in the form of only looking at the dual variables, which are the alphas. And when we did all the math, we found that the form of the primal, sorry, form of the dual had this form. Alpha I, alpha j, yi, yj, xi transpose xj. So you try to maximize this as a function over alpha. And then the constraints that we have is that alpha i's are greater than or equal to 0, I equals 1, 2 through n. And then we have one additional kind of balancing constraint that actually, if you recall where it comes from doing the minimization over W naught, which is, saying that the hyperplane does not necessarily pass through the origin. Summation of alpha I, yi equals 0. And we saw that the separating hyperplane had this form, W star, or the normal to the separating hyperplane was of the form summation of alpha I, yi, xi. And remember, the yi's are either +1 or -1. So this for linearly separable SVMs, this is the primal. This is the dual. And this is the form of the separating hyperplane. Okay, so kind of interesting, right? That it is plus alpha i's xi's for class 1 and minus alpha i's xi's of class 2 because yi's are +1s or -1. And in terms of kind of this picture, what we found through analyzing the primal dual as well as the complementary slackness conditions that happen, and if you've forgotten it, and in some sense, I'm going to do the nonlinearly separable SVM today, so that should reinforce what we did last time. Okay, so if you have points which are away from the margin, right, these alpha i's end up actually not contributing to W. So these alpha i's are all equal to 0. And we would not really have realized that if it wasn't for the analyzing the complementary slackness conditions. And then if I have these points over here, which are on the margin, okay, because my constraints are actually saying that all the points have to be on either side of the margin. So over here, it would be this, let's say this was over here and this, right? These are the points where the actual alphas are not equal to 0. In particular, they are greater than 0. Okay, so I'm just kind of doing a recap so far of what we did before. Okay, now, we are not always going to, like I said in the beginning of the lecture, we're not going to get this kind of easy data sets, right, where there is clear linear separability between one class and the other class. In normal cases, we'll get, let's say, in usual cases, we might get, we get one class over here, another class over here, okay? But there is some noise. So there may actually be elements from the other class over here, and there may be some of the pluses may actually be over here. So what do we do in this case, right? Which is the more realistic or usual case, because we may not know whether the data is linearly separable or not, okay? So last time we said that we can handle non-linearly separable data through SVMs using a very slight modification to the optimization problem, okay? So what we say is that we'll keep we went through the machinery and we arrived at the primal, which is very similar, okay? Minimize over W naught psi. So we introduce one more variable. It does not come in the objective over here. It does not come over here, right? But it relaxes each of these, and that's why it's called a slack variable. So these psi's are slack variables. So it's basically saying that, hey, instead of being very particular that each and every point should be on one side of the margin, depending upon the class label, we'll actually give it some slack. We'll say that, hey, it can actually obey this inequality up to psi. Okay. So what do I mean by up to psi? So it says that my yi W transpose xi plus W naught when we said it has to be on the other side of the margin, this has to hold, right? This is how we got the primal SVM. And now we'll just say that, oh, it's actually 1 minus psi I, and psi i's are going to be greater than or equal to 0. We do need to control that the psi i's can't be too many. So one potential constraint would be that psi I is less than or equal to a constant. So the summation of the psi i's, I equals 1 through n is a constant. Okay. And this, what you can do is you can actually take this into the objective. Okay. So remember that we can, instead of having a linear inequality constraint over here like this, we can take, plus gamma times this and move it into the objective. Okay? So they're very kind of similar. So this is then the primal. As a result, this is the primal problem. Okay, so let me write it. Minimize half W2 square plus gamma times summation of psi I equals 1 through n. Okay, such that, and again, that now let me put this into standard form. Remember, standard form is that I want all the FIX's to be less than or equal to 0. And the only reason we do it is so that we kind of have this thing about the Lagrangian and the corresponding dual variables for these inequality constraints are going to be greater than or equal to 0, right? So the constraint is, I want to write this as an inequality, less than or equal to 0 inequality. So I'll say that 1 minus psi I minus this is less than or equal to 0. So I have 1 minus psi I minus yi w transpose xi plus w naught is less than or equal to 0. So I've just rewritten this as a less than or equal to. Okay. And remember, I did not write this, but this is again over all the training data. I equals 1, 2, 2. And then again, I'll do the same thing over here. So instead of saying psi i's are greater than or equal to 0, let me write it as minus psi I is less than or equal to 0. Okay. So this is the primal that we are dealing with. Now, one thing I don't know if I may have mentioned that, why did we do the derive the dual? Well, one was to kind of get this intuition, right, about geometric intuition about what is actually happening and what my support vectors are, right? So these are the support vectors, the ones where the alphas are greater than 0, right? But the other part is that, many of the much of the software which is able to work for very, very large data sets is actually by working with the dual solution. And one of the reasons is because the dual solution, the inequality constraints are actually much simpler. This is, just a negative inequality constraint, and there's just one equality constraint, as opposed to these more complicated, n inequality constraints. And it turns out that sometimes, or many cases, that this problem ends up being quite a bit easier. And there's also another reason many times, at least from this figure, now this figure is not representative of a non-linearly separable SVM. We'll come to that later. But many of the alphas end up being zeros over here, right? The ones that are correctly classified. So sometimes you can kind of start this from the solution alpha equal to 0, and then incrementally add the alpha. So what people found is that if you do these kind of coordinate descent or descent methods or ascent methods, then you can actually get a much quicker solve. Okay. So just to kind of give you another motivation of why we look at the SVM dual, it's not just to build the intuition, but it's actually quite important for building good quality software for this problem. Okay. So I've kind of motivated again the need for the dual. So let's try to derive the dual corresponding to this primal. Okay, so I'm again going to go now possibly a little bit, not possibly, but a little bit quicker than I went last time. But we'll do all the steps. So kind of you get additional kind of exposure to this kind of material. So the Lagrangian L is now, remember it has primal variables, W naught. Okay. Oh, and psi, right? I have three primal variables. And then the corresponding dual variables. How many dual variables are there going to be? Remember the dual variables corresponding to the inequalities in the primal. So earlier, there was just one set of inequalities. So that's why we only had alphas, one set of dual variables. Now, you actually have two sets of dual variables, right? One corresponding to these inequalities and the other corresponding to these inequalities, for the time being at least, okay? We'll actually see that we'll actually be able to get rid of one, okay? So I have alpha and I have mu. Alphas are going to be, as before, dual variables that corresponding to these inequalities, and the mu's are the new dual variables now corresponding to the psi i's being greater than equal to 0. Okay, so what is the Lagrangian? Well, I took at the primal objective. So I'm just copying this down over here. So half norm of W squared plus gamma summation of psi I equals 1 through n. And then I have terms from here, right? So alpha i's times the left-hand side of fi, 1 minus ii minus yi, w transpose xi. Oh, I made a typo here, huh? This should not be there. Luckily, I have an eraser. Let's see if I can selectively erase this. Oh, perfect. Okay. Yi w transpose xi plus w naught. Okay, and then my final term over here is mu I minus psi I. Okay, but let me just write it as, I'll just take the minus sign outside, minus sign. Okay. And now we start the machinery. We take this Lagrangian and we look at the gradient with respect to W. If I set that equal to 0, this is the same thing as before, because really nothing much has changed in terms of those terms, right? I have this W, and then I have this stuff from before. Okay, it's same as before, really hasn't changed. So it turns out that W will still be summation of alpha I, yi, xi. It will still have that form. Okay. Similarly, when I take the gradient with respect to W naught, okay, I will, let's see, if I take the gradient with respect to W naught, I have basically summation of alpha I, yi equal to 0, same as before, okay? So that's the balancing constraint. When I say balancing constraint, that basically says, remember yi's are either +1s or -1. So it just says that the sum of the alpha i's for class 1 is the same as the sum of alpha i's for class 2, okay? And then the new part is the gradient with respect to psi, okay? And what is that? Well, let's see. Psi occurs over here, and over here, right? So what I get is that I get, and remember, I'm taking the gradient with respect to each psi I, so I get gamma minus alpha I minus mu I equals 0, okay, for I equals 1 to n. And what that says is that alpha I, which are my dual variables, have this form, which is equal to gamma minus mu I. Okay, so that's the new part from before. This wasn't there before. Okay, so now if I substitute this back into the Lagrangian, what I get is, well, again, it's identical to what we had done before, half of W squared. So let me write that out. Half of summation of alpha I, yi, xi. So that is W. And so I'm doing norm square, right? So half of W square. This is W is of this form, so I get that. And then I have half of summation of psi I times gamma, right? So I need to substitute gamma from here, right? So I will do, let me see. Yeah, actually, I can collect these terms, right? I can collect psi I. Actually, I don't, sorry, maybe I shouldn't have said substituted. Let me just collect all the terms from summation of psi I, right? So I have summation of psi I have gamma. And with each psi I have minus alpha I minus mu I. So I basically have summation of psi I times gamma minus alpha I minus mu I. Let me keep on kind of writing it up, and then we'll see, we can simplify it. Plus, let me write this summation of alpha I term out as before. Summation of alpha I equals 1 through n. This term I've already included in the psi I, right? I've already included this term. So what's left is summation of alpha I, yi, xi transpose times w, and w is of this form. Okay, so I can write this as minus summation of I equals 1 through n, alpha I, yi, xi transpose times, and this is w, summation of I equals 1 through n, alpha I, yi, xi. Okay, and then the one term that I have left, again, it's very similar to what I did last time. It is this W naught, right? So summation of alpha I, yi, W naught. Okay, so it's minus summation of alpha I, yi, W naught. I equal to 1 to n. Okay, and now if I look at remember, I had this balancing constraint just as before. Okay. and I have this part. So this, because W naught is common, this is going to be equal to 0, right? Summation of alpha I, yi equal to 0. And now there's another thing that happens, which is that if I look at this part now, which is that gamma minus alpha I minus mu I equal to 0, and I look over here, well, that's exactly this. So this is also equal to 0. Okay. And then I basically, if you see very similar to this, I can actually combine this, right, to give me minus half. Okay, this will give plus half of this square, and this is like same thing, except there is a minus 1 over here. So this will give me minus 1/2 summation of I equals 1 through n alpha I, yi, xi, and I take the norm square. Okay, and then this, as before, it gives me plus summation of alpha I. Okay, so we are kind of putting it all together, right? And the dual problem then becomes, remember now I'm going to maximize with respect to my dual variables. What are my dual variables? They are alpha and mu. And so I have summation of alpha I equals 1 through n. I'm just copying it from here. Okay, minus 1/2 summation of, I can write it in expanded form like I did before. This is alpha I, alpha j, yi, yj, xi transpose, xj. And my dual variables are alpha i's and mu i's, and the constraint is that alpha I is greater than or equal to 0, and mu I, which is the dual variables corresponding to the psi i's, they're also greater than or equal to 0. Okay, I equals 1 through n, and then I have that balancing constraint, which is summation of alpha I, yi equal to 0. Okay, so quite a lot of algebra, right? But again, pretty much a repetition of what we did last time, but this is the version that is used, right?
I have a question.
Yeah.
Do you also need the constraint that gamma minus alpha I minus mu I is equal to 0? Or is that a part like integrated into
Oh,
like
yeah.
the
A good point. I actually missed that, right? So and actually I was about to come to that. So this is that alpha I has the form gamma minus mu I, correct? No, what did I write? Gamma I minus mu I, right? And actually, what does that imply? This implies mu I is greater than or equal to 0, minus mu I is less than or equal to 0, right? So this actually implies that alpha I is less than or equal to mu. If I basically take this and put it over here. Okay. So it's actually quite interesting that the dual problem actually becomes the following. Maximize. I can actually eliminate the mu. Okay, because alpha I has this form, gamma minus mu I. So the maximum value alpha can take is gamma. And that's the only place where it comes in. So I can actually eliminate mu. And so this is the final form of the dual problem. Okay, such that now I have that alpha I is not only greater than or equal to 0, it's actually also less than or equal to gamma for I equals 1, 2 through n and the balancing constraint. Okay. So does that, sorry, I ended up, um,
No, that makes sense. Yeah. I also had a question on the Lagrangian before you took the dual. Can you like wherever like it's left circled psi I times gamma minus alpha I minus mu I. So I get can you go back to how you like got that part when you took out the psi I's? Like I think if you go a little bit up from
okay.
here, I guess maybe not. Like in the original Lagrangian.
Yes.
I understand you factor out the psi
Yeah.
i's, but how
Yeah.
did the alpha I term come?
So remember there was here, right?
Oh, I see. That makes sense. Yeah.
Right. So the
Awesome.
alpha i's were the dual variables corresponding to uh, this inequality constraint. So you will get an alpha I times psi I term, which is new now compared to the linearly separable SVM problem that we did.
Yeah, that makes sense. Sorry, I missed that
Sure,
psi I
sure, sure,
term
sure,
there,
sure.
but yeah, thank
Sure.
you.
Okay, but you see, like it's kind of pretty interesting, right? I mean, in a way, it's quite beautiful, honestly, right? So when we did the SVM primal and the SVM dual for linearly separable, right? We pretty much got this dual. But then when we added this nonlinear separability, if you just take a note at this, right? Just make a mental picture of this. You have an objective, summation of alpha I equals 1 through n. Then basically some quadratic term in the alphas, linear inequality, and a balancing constraint. If I just look at it, the nonlinearly separable SVM just ends up changing this. So that not only is it greater than or equal to 0, but there's also an upper bound on the alphas that they cannot be greater than or equal to lambda or gamma, sorry, where gamma is the kind of weight that is given to the slack variables compared to this. Okay, so it's actually kind of remarkable that it happens, right? And this also, like I said, it actually turns out to be easier to solve also in practice. But it actually also gives us, let's now look at, the complementary slackness conditions, and we'll realize that, again, it enhances our understanding of what has happened. Right? So let's look at the complementary slackness conditions. By the way, I know there was one question. Anybody else have a question on what we just did? Feel free to ask. Huh? So the complementary slackness conditions, remember, it's talking about both kind of the dual variables and the corresponding constraint, which says that for each I, alpha I times the FIs, where FIX is or W is less than or equal to 0, that must be equal to 0 at the optimal. So this is the first set of complementary slackness conditions, right? Remember, there are two sets of dual variables. And the mu i's are mu I sigma I, psi I is greater than or equal to 0. Sorry, equal to 0. Okay. So let's actually look at the picture, right? So we had, we have one class. We have another class, right? And remember, we have some, it's not linearly separable. So we have some pluses on this side and some minuses on the other side. So I still have a separating hyperplane, right? There's still some points on the margin or on the boundary. Okay. So just as before, and let me just color them with, different colors. So the ones that are kind of correctly classified, okay, there the alpha i's are equal to 0. Okay. From before, what we had, right? There are some points on the boundary. These points all have alpha i's to be greater than 0. But now there are other things, right? The other parts which are misclassified. So misclassified ones are, here, 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 and here. Okay. And what happens to the misclassified points? Okay. If I think about it, right, the misclassified points, let me just. Okay. So these points are misclassified. What happens for these points? Psi i's are greater than 0. And what does that mean for the complementary slackness conditions? That mu I must be equal to 0. And if I go back, remember that alpha i's are of the form gamma minus mu I. So that means that the alpha i's are actually equal to gamma. Okay. So for these misclassified points, maybe I should have used a third color, right? But alpha I is actually equal to gamma. So obviously it is greater than 0. But you can see now that, alpha i's for misclassified points are actually limited. They cannot be bigger than gamma. So even if there's like a huge outlier or so, right, which is somewhere over here, like a negative over here or a positive way away from the margin, right? That outlier does not actually affect your decision boundary too much. It's capped at gamma. Okay, and remember that my solution is of the form W equal to summation of I equals 1 through n alpha I, yi, xi. So the support vectors are now essentially, not just support vectors, but points on the wrong side of the hyperplane, right, of the margin. So they are the points which are on the boundary plus the misclassified points. Okay, so let me just kind of recap, and then we'll move on to kernel SVMs. Okay, but I'm just going to write it over here because I'm going to make some points. Okay, so SVM primal is minimize over W naught psi half of W square plus gamma summation of psi I equals 1 through n, such that psi i's are greater than or equal to 0, I equals 1, 2 through n, and then 1 minus I minus yi W transpose xi plus W naught is less than or equal to 0. I equals 1 through n. So that's my SVM primal. Okay, and then I'll write the SVM dual over here, right next to it. This is maximize over alpha. Remember, we were able to get rid of the mu variables. Summation of alpha I equals 1 to n, minus 1/2. Summation I equals 1 through n. Summation of j equals 1 through n. Alpha I, alpha j, yi, yj, xi transpose xj, such that my inequality constraints again on the dual variables are simpler, non-negative, and a capping constraint. Cannot be bigger than gamma. Okay, summation of alpha I, yi equals 0. Okay, and the reason I've kind of written it again over here is that I want to point to two things, okay, which are actually both quite surprising. What we will see later on is today, not when I say later on, just I'll talk about it at the end of the lecture. You can actually think of this as regularization. And this quantity has actually a loss, classification loss, and it turns out that this is something called the hinge loss. And we'll come to that towards the end of the class. And then the other thing that I want to say is that you can actually write the dual, and actually that's one of the reasons why the dual is important, very important, is when we look at kernel SVMs. So you can see that this is only dependent on the inner product, right? Xi transpose xj. Okay, and you can actually take this and you can extend it, and I'll talk about it in just a few minutes, is that I can take this and instead of just using a normal inner product, I can use a kernel function, which is actually an inner product on a non-linear feature space. Okay, so I've written something where you might have no idea what I'm talking about. So let's discuss it. Okay, but another reason why the SVM dual is very critical is because I can just take this, change it to this, and then I can just do this problem. Whereas if I was to do the SVM primal and I was to take X and map it to phi explicitly, this problem will really blow up in the dimension of W. Okay, so let's see what I'm talking about. Okay, so let me make a few definitions. Okay, and I'll actually show you how to also write the SVM. You see how long it takes me to write the SVM dual. Let me actually write it in a much more compact form. Okay, so let me define. Oops, let me go back to my original pen color. Okay, let me define X. So let me stack up all the training data as the columns of this matrix X. Okay, this is something that we did, for example, in least squares problems. Let me denote a diagonal matrix with the labels, with the y's. Okay. If I now look at the matrix, so see I have xi transpose xj. If I form the matrix x transpose x and I look at the ijth element, that is exactly xi transpose xj. Okay, and sometimes this matrix is called the Gram matrix. Okay, let me also use another notation, which is E, which is the all ones vector. The all ones column vector. And this means that E transpose is all ones row vector. Okay, given this above notation, given the above notation, the dual SVM can be written in a very, very compact way. The dual SVM can be written as, well, I have summation of alpha I, right, over here. Summation of alpha I, well, I can just write it as, so first, of course, there's a maximization problem over alpha. Summation of alpha is just E transpose alpha. E transpose is the vector of all ones. If I take an inner product with alpha, okay, alpha is column vector of alpha 1, alpha 2, alpha, okay. And the second part, which looks very kind of, it's a quadratic function, right, in the alphas. I can actually write it as a quadratic form. What do I mean by that? It is minus 1/2 alpha transpose, y transpose, x transpose, x, y. Okay, so just take a minute and see, and of course I forgot the alpha at the end. This quadratic form, if you expand it out, is exactly equal to this. And I've just written y transpose. I could have just written y because y is a diagonal matrix. Y transpose y, y transpose equals y. Okay, so that's the power of kind of, linear algebra, that sometimes you can get rid of all these hairy indices and write things in a very simple form. Okay, and if I and then what do I have? I have inequality constraints. 0 is less than equal to alpha is less than equal to gamma. I can write that as, alpha, the vector alpha, right, is greater than equal to the 0 vector and is less than equal to gamma times the E vector, all ones. And then alpha transpose y equals 0. So I've just written things very compactly. Okay, and if I further, I write this matrix as Q. This becomes equal to E transpose alpha minus 1/2 alpha transpose Q alpha. So you can see very clearly now from here that you have a quadratic optimization problem. Objective is quadratic, and you have linear inequality constraints. And further on, you can actually show that Q is a positive semi-definite matrix because it has this form, x tilde transpose x tilde, where x tilde is x times y. Okay, well, I've kind of just introduced notation and just written the SVM problem a little bit more compactly. Okay, and there's a reason why I'm doing that. So now let's move on to the classification problem. Okay, so classification problem, let me kind of give you a data set, which is, lies, let's say you have a data set which is in two constant, where class 1 is one concentric circle and class 2 is a second concentric circle. Have you seen this data set somewhere else? Or? No? okay? And sorry, my circles are a little squished, but they're supposed to be circles, okay? And here now you can start seeing that even though the approach that I took said non-linearly SVM problem, it's probably not a good idea to think of a hyperplane over here and, you know, penalize these points for being on the other side of the hyperplane. That's just a bad model for separating this kind of data set. And, you know, the good model would be, what is a good surface that separates the circles from the pluses? Well, it's just this quadratic surface, right? This is a circle through the middle, right? Everything inside this red circle can be classified as, you know, belonging to this class, and everything outside can be thought of as belonging to the positive class. And if I think of this equation, right, this equation is just x1 square plus x2 square equal to R, right, where x1 and x2 are the two coordinates, right? Sorry, I'm changing notation a little bit, but x1 and x2 are the two coordinates right now, okay? So this is not linear in X, okay? So what can one do? So here is the trick that one can do. Suppose you have X in RD, so D dimensionals, okay? So in particular, D equals 2, we can look at X equal to X1, X2. Let me call this the input space. Okay, what I can do is I can take this and I can map it to a nonlinear feature space. Okay, so I'll map it to a feature space. So phi is a map that goes from input space to feature space. Input space is RD, and typically this will be R D prime, where D prime is greater than D. Okay, and how will I do it? So for example, I can take this as, I can construct a constant feature, square root 2 x1, square root 2 x2. So these are the linear features, which are same as before. And I can construct quadratic features. So what I've done over here is I've gone from 2D to 1, 2, 3, 4, 5, 6. So D prime equals 6. It's not like I'm using any new information. I'm just constructing a feature space from the two features that are given to me. So for example, if I have this data set, each training data would be described by two coordinates and the corresponding y, right? What I've done is I can actually represent it as a 6-dimensional feature space, okay? And here's the interesting part, right? That if I now look at this separating surface, it is not linear in X, not linear in the feature space, but it is linear in phi of X. So in principle, what you could do is you could, you have this problem, right? So you can either solve these problems in input space, but you'll only get a linear classifier in the input space, linear decision boundary in the input space. The other is I can change this X to be phi of X, right? So instead of X is being 2-dimensional in the example that I gave of the two concentric circles, phi of X would be 6 dimension. And I can solve it. Okay. But the problem is you've taken like a 2-dimensional feature space and kind of blown it up, made it much bigger, right? How many features are there by in the construction that I have? Here I went from d equal to 2 to d prime equal to 6, right? I'm basically taking every possible combination. So you would go from d to d square. That's a big blow up. All of a sudden, your d is already, let's say, millions of features. Suppose you have a very big problem, right? And then you go from 10 to the power 6 to 10 to the power 12 features. Much, much bigger problem, right? Trillion features. So that's just too expensive. And so one of the beauties of kernel SVM, which I'm going to talk about, is that you can actually just solve the problem in d dimensions, 2 dimensions in this case. And here's the crucial observation. The crucial observation is if I take phi of x, I take phi of x prime. Okay, so if I have x prime equals x1 prime, x2 prime, so that's another data point. Sorry, I don't know why I did transpose. X1 prime, x2 prime. Okay, and I say that phi of x prime equals, same function, right? So 1 square root 2 x1 prime, square root 2 x2 prime, x1 prime square, x2 prime square, and then square root 2 x1 prime, x2 prime. The interesting thing is that if I take the inner product, okay, between these two, this and this, let me write that. 1 square root 2 x1. Maybe I should just write this below. Okay, so phi x transpose phi x prime is equal to, I'm just going to copy this. So it's 1 square root 2 x1, square root 2 x2, x1 square, x2 square, square root 2 x1, x2, and then 1 square root 2 x1 prime, square root 2 x2 prime, x1 prime square, x2 prime square. Please keep me honest. I'm almost certain I probably made a typo somewhere. Square root 2 x1 prime, x2 prime. Okay, and if I multiply this out, let me do it. So 1 plus 2 x1, x1 prime plus 2 x2, x2 prime plus x1 square, x1 prime square plus x2 square, x2 prime square plus 2 x1, x2, x1 prime, x2 prime. Okay, and you can see that you can write this as 1 plus, I can, write this as 1 plus x1, x1 prime plus x2, x2 prime square. This is a very crucial observation. Okay, so that means that I've written it as 1 plus x transpose times x prime square. And this computation, so remember this computation is in 6 dimensions, but I can actually do this computation in 2 dimensions. Because x is 2-dimensional, x prime is 2-dimensional, but phi of x was 6-dimensional. So in general, in the quadratic, we call this the quadratic kernel. So this is a polynomial kernel of degree 2. That is a quadratic kernel. Okay, and we'll denote this as k of x, x prime. So here is the kernel trick. You basically can write k of x, x prime as phi of x transpose phi of x prime. This computation is in d dimensions. This is in d prime dimensions. And d prime can be d square, can actually be d cube, and actually in some cases it actually is infinite. With the, let me talk a little bit about kernel. So in the Gaussian kernel, this actually turns out to be infinite dimensions. But the beauty of this is that you never need to find this explicitly. You never need to form explicitly this very, very high dimensional feature space. So examples of kernel functions, okay, is the, let's say, the m degree polynomial. Which is k of x, x prime is equal to 1 plus x transpose x prime to the power n. And we looked in detail at m equals 2. So with m equal 2, phi of x was d square. But for general m, this is actually d to the power m. So just think about how expensive it will be, right? Not just going to d square, but to d to the power m. Okay. And then one of the most widely used kernel functions is the radial basis or Gaussian kernel. Radial basis or Gaussian kernel. And that is k of x, x prime is actually e to the power minus x prime squared divided by c. C is a scale parameter. And the reason why this is very important is that what you can do is you can take the dual problem and just replace this inner product with the kernel function. And what you can do is you can devise methods, right, which actually never involve explicit enumeration of the feature space. So you never need to compute phi of x. All the computations that you do involve k of x, I x j. So as a result, this computation can be done in, some time that is depends on n, but never on d prime. So that is another reason why SVMs were so powerful, because you could actually devise pretty good software for these kernel SVMs. Okay, so like, let me kind of talk a little bit about, a data set. This is the two concentric circles data set. There's also like a popular data set, which is what's called the XOR data set. So you have class 1 over here, or class 0 over here, and then you have class 1 over here. Okay, and this is called the XOR data, because if I look at the coordinates of this is 0, 0, this is, what is it, 0, 1, this is 1, 1, and this is 1, 0. Basically 0, 1, 0 XOR 1 is class 1, 1 XOR 0 is class 1, 0 XOR 0 is class 0, 1 XOR 1 is class 0, right? And you can obviously see that there is really no linear separability over here, okay? I think that's about the end of what I'm going to talk about in terms of SVMs. They are very, very good software packages if you want to ever use SVMs. Liblinear, okay, that's linear SVMs, linear SVMs, but non-linearly separable SVMs. And then there is libSVM, which can handle kernel functions. Okay. Any questions? Let me just conclude by, let me just take a couple of minutes of your time. I might run over by a few minutes. In regression, I'm kind of concluding now by kind of saying that there's actually a common framework between classification and regression, right? We studied these two problems before. In regression, it was very clear, right, that we had a loss function, for example, quadratic loss, least squares, and then we had regularization. We have spent a lot of time talking about rich regularization, right? Something that you did in your homework. Expect some questions in the midterm on that. Okay, and then we talked a little bit about Lasso. Okay, classification, we have taken a different approach, right? We talked about logistic regression, we talked about SVM. It's not clear that it actually has this structure, but it turns out it does. If you look closely, then classification can also be written as loss function plus regularization. Okay, and the regularization again can be L2, L1. Okay, but if you look closely, then you'll see that I can have like a logistic loss, which is log of 1 plus e to the power minus y, y hat. Y hat is the predicted variable. And again, it may not be easy to see, but even in the case of SVMs, you have something called the hinge loss, which is maximum 0, 1 minus y, y hat. Okay. And this comes from the observation of psi i's, right? So if xi is correctly classified, then the psi I equals 0. If not, it is psi I. Okay. So, and you can see it from over here. Over here. Okay. So psi I sometimes will be greater than 0. But if it is exactly classified, right, then the psi i's will actually be equal to 0. Okay. And so what you can show is that if I plot y hat on the x-axis, well, ironic that y is on the x-axis, but that's what it is. If I have -1, 0, +1, okay, then hinge loss is, maybe I should just use the green. Hinge loss is this function. Sorry, the exact loss is this. Okay, the exact classification loss is this. Hinge loss is 0 over here, and then linearly, so it's like a hinge function. It hinges over here. And logistic loss, okay, is something that is an exponential and goes like this, or log of this exponential. So this is logistic loss, and this is inch loss. Okay, sorry, I had to go through this last part a little quickly. I'm happy to explain it a little bit more next time we meet.